Hey guys, we are citizen scientists who work with the Globe Mosquito Habitat Mapper and land cover datasets.
I'm Prachi Engel.
I'm Mateo Kimura.
And I'm Pratham Babaria, and we all worked with Rusty and Pater this past summer through the NASA SEAS internship. Through this program, we grew familiar with the Globe Observer API, and together we explored and evaluated the Globe data quality and accessibility.
During our internship, we explored solutions to two barriers in the use of citizen science data. The first was addressing the common issue with environmental monitoring projects using an opportunistic sampling. What story can these data tell when you can't describe the significance or relationship of individual observations? So that's where our solution comes in. We employed a structured sampling design at each study site. By adopting a pixel and nesting our samples, spatially coincident data from diverse sources could be compared more easily. The sampling design enables field-based observations to be compared to high and medium resolution data obtained by satellites. The second barrier we experienced in using GLOBE data in our work was determining the fitness of use of the data in our projects. Our project focused on automating processes that will reduce time barriers in the application of Globe Observer data to real research questions. The red box is where we come in. We created a Python procedure where users pull data from the Globe API. They can filter by their protocol, like mosquito habitat mapper or land cover, date range, and location. We then go in to clean up their data, removing redundant information, establishing logical naming conventions, and standardizing reported data so that null values are the same across the board, and there's only one value per column. After cleaning the data, we then added quality assurance flags, summarizing the data for future users to better visualize their data quality. We also began ranking data observations by their usability. To do this, we created completeness scores that show the user how much key information a specific observation can provide, allowing users to quickly filter out observations that lack the key components they're looking for. We then provided diagnostic graphs for users to quickly visualize their data sets. Lastly, we created an algorithm for users to choose which specific criteria for the data set they wanted prior to download. For example, in the mosquito habitat mapper datasets, users could specify a specific mosquito genus and get those observations. Ultimately, we plan to implement these pre-processing procedures into a new beta-vetted data access portal. This would significantly increase the accessibility and usability of Globe's rich citizen science datasets, encouraging future citizen scientists to engage with our data for their own scientific questions. We found a few common data problems in the Globe datasets. Sometimes the column names were not very intuitive, like in the mosquito habitat mapper and land cover datasets, there were two sets of location data with non-intuitive naming conventions. We also found that some columns were redundantly homogeneous, since all the cell values had the same value. Across the columns, we also saw inconsistent null value reporting. We also saw that some columns were overly packed with more than one value per field. To explain this further, a good example would be how land cover classifications of a photo were listed as a dictionary in one column. This makes it really difficult to parse out key land cover classifications. Another problem we found was that some columns had unreasonably high number of decimals. Decimals take up a lot of memory, so we realized we needed to round data appropriately. All these aforementioned problems limit the GLOBE dataset's accessibility and overall quality. So we came up with a few solutions. We removed and renamed columns appropriately, unpacked dense columns with more than one field entry, standardized null values, and appropriately rounded numerical data. We also built in attribution validation procedures where we flagged any entries with extremely extraneous values. These quality assurance flags also included photo counts and other data-specific flags. For mosquito habitat mapper, we flagged extraneous larvae count, whether the user identified a mosquito genus, if there was a reported water source, and other key metrics. For land cover, we flagged whether users inputted land cover classifications for each photo direction. We also built in completeness scores that can help future users filter out their usable data. As a future extension, we could allow users to weight specific parameters, which would better enable dataset personalization. Lastly, and perhaps most importantly, we built a giant metadata appendix for our dataset, denoting what each column meant, what was the data type, what were field entries, and how we denoted extraneous or empty values. This helps future users better understand and use our data projects. Overall, our solution increases the accessibility and usability of Globe's legacy ecological datasets. This can help drive future models.
Now, as we look to the future, there are a few things that we should keep in mind. We need to continue refining and updating our data cleanup and quality assurance procedures. We also need to continue following the PPSR citizen science metadata best practices. And we also need to remain vigilant for new data peculiarities and refine our data validation procedures to flag new extraneous entries. Our next steps are to enrich our globe datasets with satellite measurements. Linking citizen science observations with the satellite perspective can help us develop more robust models for mosquito and ecological behavior. Here's an example of how users can filter out less usable data for their own specific scientific questions. Let's say a user is trying to build a machine learning model that classifies mosquito larvae from a photo. For this project, they would need to use observations with a larvae count greater than 0 and a photo count greater than 0. On the left, we have the raw mosquito habitat mapper data. As you can see in the top left, larvae count distribution, there are many observations with a null larvae count represented with a negative number, and there are observations with 0 larvae count. In the bottom left, we also see that there's quite a few observations without any photographs. The user would want to remove these unusable entries. So with our pre-processing procedures, the user could download mosquito habitat mapper observations with a positive larvae count and at least one photo. Now if we look to the right, we get a visual verification that our filtering worked. The user now only has the observations he or she needs. There are no entries with extraneous larvae counts or no photos. Now the user can go and more easily build their machine learning model.
On the left, we have multiple bar graphs displaying the distribution of land cover photo statuses on a log scale. The different photo statuses include valid photos, rejected photos, and fields without photos. Since we had to use a log scale to better showcase the distribution, we see that our spread is extremely wide, highlighting that some users would greatly benefit from filtering out observations without valid photos. Below the bar graph, we have a histogram of mosquito habitat mapper completeness scores. This cumulative completeness score is the percentage of all MHM columns filled out by a specific observation. As seen in the graph, there is a high center and moderate spread in completeness, indicating that mosquito habitat mapper observations are mostly all filled out, but there is some diversity in observation completeness. If we look at MHM completeness on a more global scale, we see here on the map that the globe MHM datasets are pretty diverse, both geographically and in terms of quality. In this map, we also see just how large Globe Observer's reach really is. The organization samples from many diverse environments. Overall, Globe's mosquito habitat mapper and land cover datasets are not only rapidly growing in size, but also in applicability towards scientific research. Our data pre-processing protocols will help further the accessibility and usability of this data, so more researchers can use Globe datasets to explore unique scientific questions. We plan to continue this work in summer 2021 and are working with the IGES team to provide access to pre-processed data products to the SEA's mentors in the Earth Explorer research internship next summer, enabling them to spend more time on research questions and less time on data processing. Data products from our project are currently available through the Earth System Data Exploration Portal beta, developed by IGES to support SEA's research interns. The SEA's 2021 high school internship team, Earth Explorers, will have access to this portal to extract and use pre-processed data using algorithms we created as part of this project. If you're interested in contacting us further, please feel free to reach out to our cells. And if you would like to learn more about the Globe Observer dataset or access Globe data, please visit these links to the Globe API and IGES portals. Thank you all for attending our presentation.